In Chapter 3, we learn about fields due to charge distributions. And so that means instead of having individual charges, we have lengths of charge, or circles of, or spheres of charge, or shapes of charge. And so how do we figure out what the electric field is due to those kinds of charges? We're not going to go into a lot of detail in Chapter 3. So, but I did want to bring up a few things that we would like you to know from this chapter. And one is that the way you calculate the field for a bit of charge, right? And let's say I have a distribution of charge, say a sphere, and I want to calculate the electric field due to that that entire sphere of charge. Well, what I can do is I can break my sphere up into little teeny tiny bits, and then each little teeny tiny bit will have a field given by Coulomb's law. So we can use this Coulomb's law to figure it out. And then what we do is we integrate over dE, we integrate this over dq, and so we have to think about, if I think about a sphere, I'll have to integrate over theta and phi, and the integral is pretty involved, and so we didn't really want to get bogged down in the calculus in this chapter, but we wanted you to remember actually the way you would calculate charge for a charge distribution, right? An object that has a charge. And so that I just wanted you to let you know that's how you would do it. And so let's talk about a charge for a minute. When you do go through the integral to determine what the field is due to a spherical shell of charge, we find that that outside of the sphere we have the electric field is equal to kq. Q represents the charge on the sphere over r squared times the unit vector r, and that's the same formula that we have for the field due to a single point charge. And so that's pretty surprising to find that the charge outside here, far away from that sphere, would be given by that same formula. And then we also find the surprising result that inside that hollow spherical shell, remember it's hollow, that our electric field is equal to 0. So remember this is called a spherical shell of charge. We also want you to know that the electric fields of a conductor, that inside a conductor the electric field is 0. So if I look here at this example, I have a donut. Inside the donut, my electric field is 0. Inside here, where there is no conductor, there's air, but there's a charge inside, I have an electric field, right? I have an electric field due to this charge. When I get to the conductor, that field goes to 0, so inside it's 0, and then when we get outside, again, there is an electric field. Any good conductor will move the electrons around so that there is no electric field parallel to the surface. So the electric field for a conductor will always be perpendicular to the surface. And you can see that here on this sphere, right, that the electric field is always perpendicular, pointing away from the surface, or away from or towards, but it's in the same direction as R, or the perpendicular to that surface. We can use that quality of conductors to provide electric shielding. So here we have two plates, and they produce a field, which we'll talk about in just a minute. But we can see if we put a conductor inside of them, that conductor, if there's no charge inside of here, right, protects whatever would be inside from that electric field. So the conductor that's one of the uses of a conductor, is to protect it from the field, to protect something that we put inside from the field outside. Let's talk about parallel flat plates, and we find that for parallel flat plates that the electric field between the plates is given by sigma, this surface charge density, times n. N means the normal to the surface over epsilon naught, and that's only in between the plates. So in between the plates we have an electric field, but outside of those plates we have 0, we have no electric field. And I just want to show you why just for a moment. If we look at these two plates and we just think about the positive plate first, we would have an electric field that looks like this. It would point away from those plates, and it would point away from the plates over here. And now if I think about these, the negative plate, my field is going to point like this. Right, so I can see here that outside my field is going to cancel here, and it's going to, and I'm sorry, these these the electric field here should point towards this plate here, right? It should point towards here, not away. So these vectors here coming out from the positive cancel with the vectors going towards the negative. So out here, basically, all of the fields cancel with each other. But what about in between? Right? If I think about in between, right, I have the electric field that looks like this here. And then I also have the electric field that's pointing this way towards this negative plate. All right, so let's blow this up a little bit, right? I have this field here due to the positive. And then if I think about the negative, right, it's going towards the negative plate. So we can see that the field here and between the plates adds just because of the direction of the field due to these plates. And so that's why I have that sigma, let's look at the formula again. So sigma over epsilon naught times n, the surface normal, for parallel plate capacitors. So this is what the situation we have in between, right? We have an electric field, and this doesn't mean it goes outside of the parallel plate capacitors. It's just telling you how big the field is at this point right here. Right outside of the parallel plate capacitors, we have 0 electric field.